So last time we spoke, we talked about graphing exponential functions. This time we're going to graph logarithmic functions, and logarithms are just the inverses of exponentials. So it's basically the same graphs we did previously, just with x and y traded. Although I'm going to explain it with how you would know what kinds of numbers to plug in. So back when we did our exponential functions, I just plugged in like from -1 to 2 or -2 to 2, or just kind of a few little central numbers in order. But this time we want to be plugging in what we got out before. So with logarithms, when you're trying to figure out what numbers to plug in, you want to use numbers that are powers of the base of your logarithm. So for example, this first one is a base 2, which means we would want powers of 2. So 1/2 is a power of 2, because it's a -1 power, right? If we do 2 to the -1 power, we get 1/2. And then 1 is always a power of any base, because anything to the 0 power is 1. So that's just your intercept that you always want to have. And then 2 is a power of 2, because 2 to the first power is 2, and then 4 is a power of 2, because 2 to the second power is 4. So I chose my x values by choosing numbers that were powers of the base 2. So 1/4 would be another one, 8 would be another one, 16 would be another one. So let's graph these and see what's happening to our graph compared to when we did this as an exponential. So we're going to go to the point 1/2 -1, and then 1 0, and 2 1, and 4 2. So here's what our graph is looking like. Now if we were to go smaller and smaller, like 1/4, that would be a -2, because that's 2 to the -2 would be 2 squared is 4, but 1/4, to get the reciprocal, we have to have the negative. So that would be coming in closer to that y-axis, but not actually reaching it. These numbers would keep getting smaller and smaller, like 1/8 -3, 1/16 -4, but it's never going to get to 0. It's just going to be smaller and smaller and smaller fractions. So right here, this is what our graph would look like. Now these are kind of hard to graph and see properly with technology, because it looks like the graph sometimes with technology is just ending right here at the y-axis, and it's not really. It's just that graphic technology has a really hard time showing when there's an asymptote. So that's just indicative that there's an asymptote there. We've got our intercept at 1 0, and I don't know if this looks familiar at all from the exponential we did that was like it, but here's the exponential function we did yesterday that had 2 to the x power, and we plugged in the numbers from -1 to 2, and we got these various numbers with this shaped graph with our asymptote at y = 0. So now we've switched that around. It's the inverse. So the x values have become our y values, and our y values have become our x values. The x's and y's have traded. The y-intercept is now an x-intercept. The horizontal asymptote is now a vertical asymptote. Everything has just traded. All right, let's try log base 5. Now, I was already mentioning this. How do you choose the numbers to plug in for x? Well, you want to choose numbers that are powers of your base. So base 5 would have 5 to the first power would be 5, 5 to the second power would be 25, 5 to the third power would be 125. Now those numbers get really big really fast. So don't forget, you can also do anything to the 0 power is 1. So 1 is always an excellent number to choose to plug in for x. And then, remember, your negative powers give you fractions. So 1/5 would be to the -1 power, and 1/25 would be to the -2 power, etc. Okay? So I've chosen numbers that are powers of the base 5. Okay, so log base 5 of 1/5 is -1, because the power that turns a 5 into a 1/5 is -1. Log base 5 of 1 is 0, because the power that would turn a 5 into a 1 would be 0. Log base 5 of 5 is 1, because the power, a logarithm is an exponent, and the exponent that would turn 5 into 5 is just 1. And then 25 is not even really going to fit on my graph, but just for good measure, I threw that one in there. So that would be 5 to the second power. Okay, let's go ahead and sketch those over here. So we have 1/5, -1, 1, 0. So see how we're always getting that x-intercept this time at 1, 0 instead of a y-intercept at 0, 1, and that's because these are the inverses of those exponentials. Then we have a point at 5, 1, 1, 2, 3, 4, 5, 1. And 25, 2 doesn't even fit on my graph, so I'm going to ignore that one. And don't forget that there's a vertical asymptote here, because we could plug in smaller and smaller values that are powers of 5, 1 over 25, 1 over 125. And that's just going to get our graph closer and closer and closer to the y-axis without actually crossing it. So something to this effect here. So what do you notice about the difference between the graph log base 2 versus log base 5? Log base 2, it is a lot taller than log base 5. Log base 5 looks like it's been, kind of vertically compressed a little bit. But that's just in a difference of the bases and how that changes based on the base. The same shape, they're the same basic shape, same asymptote, same x-intercept. It's the base makes that point kind of a different place. Like this point right here is at 2, 1 because the base of that logarithm is 2. Whereas this one is going to have a point at 5, 1 because the base of that logarithm is 5. If it was base 10, then it would have a point at 10, 1, and it would even be a flatter graph. Okay, what happens if we have bases that are fractions? This is kind of unusual to do that, but it still can happen. And it's basically the equivalent of a reflection. Let's look and see what happens. So our base is 1/2. 1/2 to what power is 1/4? I chose values for my x values just based on my base so that they are powers of my base. So like 1/2 to the what power is 1/4? Well, that would be a second power. 1/2 to what power would be 1/2? 1/2 to what power would be 1? Well, that's always 0. Anything to the 0 power is 1. 1/2 to what power would be 2? So that would require that the fraction 1/2 be flipped over to a reciprocal. And in order to do that, we need a negative exponent. And then 1/2 to 4 would also be a negative exponent, but then squared. So -2. This process of figuring out what numbers to plug in and getting those numbers out is all about this little last video we did yesterday when we were practicing what logarithms are. Remember, a logarithm is the exponent. So the more familiar you are with how to work through logarithms, because you're literally finding exponents, the easier it's going to be to figure out numbers to plug in for your graphs. Okay, so let's go ahead and plot these points. So I have a point at -1/4, 2. It's not negative. I don't know why I said negative. Positive 1/4, 2. And positive 1/2, 1. And positive 1, 0. And 2, -1. And 4, -2. What has happened from the graph right above it, where our base was 2? Now our base is 1/2. What do you notice about this graph up here compared to this graph here? Other than I didn't do very well connecting the dots. Hopefully in the graph itself, you can see that it's basically been reflected over the x-axis. And that's because the base 2 versus base 1/2, the difference between this exponent and this exponent would be putting a negative on it, right? So it's changing all of our positive values going above the x-axis to negative values below, and vice versa. So how this was approaching the asymptote toward negative infinity, it's now approaching the asymptote from positive infinity simply by taking the reciprocal of the base we had previously. So changing the base of a logarithm to its reciprocal creates a reflection across the x-axis. Okay, kind of the same here. Let's just throw these in really fast. So 1/4, base 1/4 is to the first power. 1/4 to what power is 1? Well, that's always 0. 1/4 to what power is 4? So that's -1. That's just our reciprocal. And then 1/4 to what power is 16? So that would be flipped over and squared. So -2. So again, we get like 1/4, 1, 1, 0, 4, -1, and 16 isn't even going to fit on here, but we get the idea that we get this much shallower graph. It's not stretched as much because our base is, in this case, it's smaller, but it's the reciprocal of a number that's bigger. So when we saw these earlier and saw that our base 2 compared to our base 5 is much flatter than base 2. So it's kind of the same idea here, base 1/2 versus base 1/4. Okay, let's go ahead and look at these properties then of logarithms. So y equals log base b of x is a logarithmic function with b greater than 0 and b not equal to 1, where b is called the base. F is a one-to-one function, and if the same base of a value is equal on each side, then those arguments must also be equal. So that's a one-to-one property that we're going to be able to use with logarithms when we get into solving them. Okay, so the domain, if we look at these graphs, was our domain all real numbers like it was with exponentials? No, it's got that asymptote. So our domain is going to be from 0 to infinity. And then this time the range is actually going to be from -infinity to infinity because it's going to go completely from the bottom to the top of the graph. This time, instead of a y-intercept, we have an x-intercept at 1, 0. And our y-intercept doesn't exist because there's an asymptote there. And we have a vertical asymptote at x equals 0, which is also the y-axis, correct? So if our base is greater than 1, we get a graph that goes toward the asymptote in the negative direction. But if our base is between 0 and 1, we get a graph that goes toward the asymptote, toward positive infinity. So these are just kind of reflections of each other over the x-axis.